Okay, so the test, so I talked about the results, but here we go. Okay, so the first question says to use two different methods to describe why the cos of pi over 2 minus theta is equal to sine theta. The test. Maybe. Here we go. So the two different ways to describe why that statement is true. One was that is the cofunction identity. The idea that in a triangle, a right triangle, if one of the angles is theta, the sine of that angle is going to be equal to the cosine of the angle in the other part of the triangle, since all of the angles in the triangle have to add to pi radians. The other one could have been explained by transformation. So either transformations there or the cofunction identity. Question number 2 is, obviously I didn't elaborate on the question, so I had to accept that as an answer. Sine theta, if this is theta, this would be pi minus theta. Sorry, that's not a minus sign. Let's try that again. Cool. So the sine of this angle here and the sine of this angle here are the same because of the cast rule. Both sine and sine is positive in both quadrants. So it's not true that sine of pi minus theta equals the negative sine of theta. It just equals sine theta. Question 3 was to use the compound angle formulas. You just had to plug in the values there. I think most people did okay there. Does anybody want to see that? Yeah, I was going to say A was pretty straightforward, I think, for most of you. So let's have a look at 3B. 3B looked like this. So then from here, we had to use the compound angle formula for cos. The addition of two angles is the same as cos x cos pi over 3. And because we're doing a sum in here, we're going to subtract. I'm not going to have enough room here, but that's okay. Sine x sine pi over 3. So that this part right here corresponds to this. We do the same thing here for sine, so we're going to have to subtract from that sine x cos pi over 6. Did I write the question down wrong? Looks like pi over 6. Why should it be pi over 3? Well, they didn't switch. This part was for this part, and this part's for here. Pi over 6? That's the question, right? Unless I wrote it down wrong. Okay. I totally lost where I was here. If you made a mistake here, it's probably that you forgot the brackets. Kind of important because we need to distribute that negative sign. Well, I have this part and this part. So I just can't fit it all in one line. That's why it's longer. So the cos of pi over 6, what's that, a half? So this part right here is equal to 1/2 cos x. And then the sine of pi over 3 is going to be, what's that, root 3 over 2? So we'll have a minus root 3 over 2, 3 over 2 sine x, minus cos of pi over 6 again is a half, so this is 1/2 sine x. And then we'll have to subtract the sine of pi over 6, which we said was root 3 over 2 cos x. Is that okay so far?
Okay, what I don't get.
Yeah.
So the cos x plus 3, isn't that, so that's cos a plus b, or x plus y, right?
Okay.
So shouldn't it be cos x cos y, which is pi over 3 minus sine x sine y? Shouldn't they both be pi over 3?
Oh, sorry, you're talking about this one? Yeah, you're right. I did make a mistake there. Thanks, Leslie. Yeah. Which is going to change our answer down here somewhere, right? Did I do that right? Now the cos of pi over 3 is root 3 over 2. It looks to me like there's a root 3 over 2 cos x and a negative root 3 over 2 cos x. And I guess what's left is a negative root 3, having a hard time with 3's today, over 2 minus 1/2. I think that's right. Negative root 3 over 2. Oh no, this should have been a root 3 over 2.
Positive 1/2 cos x and a negative 1/2 cos x and then 2 negative.
Yeah, it's not those that go. It's this right here. Because the sine of pi over 6 is a half. Sorry, that's my mistake. Here, I guess I'll just do this. So this right here should have been a half?
Yeah.
Yeah.
That's the first one.
Yeah. That's okay.
1/2 cos.
As 1/2, right, because we did I wrote down the angle wrong, of course.
And then the 1/2 side x is actually a negative.
This is a root 3 over 2 because we messed up the angle. Well, that makes it even easier then, because this is a root 3 over 2 minus a root 3 over 2, so there's negative 2 of those. There you go. Okay, question number 4 is probably worth doing on the board. A lot of you messed up with 4, so let's have a quick look. I'm going to separate sine x and sine y so we can do the work that we need to do. If we know that the sine is 4 over 5, the sine of x is 4 over 5, we're asked to find the sine of x plus y. It's sine x cos y, thank you, plus cos x sine y. So in order to answer this question, we need to know what the sine of x is. We have that right here. We need to know what the cos of y is. We don't have that. And we need to know what the cos of x is, and we don't have that. And we need to know what the sine of y is. So let's do a little bit of work here. If the sine, sorry, I'm just going to close that door. If the sine is 4 over 5, we'll call this x here. This becomes 4. This is 5. Pythagorean Theorem, that side's 3. So the cos of x then is 3 over 5. And the tan of x is the opposite over the adjacent. What's that, 4/3? I guess we don't need tan though, do we? Because we're just plugging into here. Do the same thing with y. If this is y, 12, 13. This has to be negative. This is going to be 5. So the cos of y is going to equal the, this is backwards. Sorry, guys. Y is over here. So the cos of y is going to be the adjacent over the hypotenuse, which will be 5 over 13. And just to make sure, it said that the y is in the 4th quadrant, so we know that the cos has to be positive. We're looking good here. And then it's just a matter of plugging in values. Now, a few of you, when you tried to plug in your values, you actually plugged in, the 5 over 13 or the 4 over 5. Guys, thanks. Into x. It's not x that equals 4 over 5. It's the sine of x. So we need to replace this whole thing with 4 over 5. We know that this is 4/5. Oh, you were done early. Wow, compared to your math test, yeah. Oh. Cos of y we know as 5/13. And then cos x is listed over on the board there as 3/5. And sine y is negative 12 over 13. Now it's just a matter of doing a little bit of fraction work. Just met with some grade 8 teachers today, talking about how important fractions were. It's funny how simple this seems to you guys now compared to when you were in grade 8. Multiply the numerators. What's that? 20 over 65 minus 36 over 65. So the sine of x plus y, negative 16 over 65. Any questions with that one? Question number 5 says to explain how to evaluate the cos of 2a if you know the value of sine a. Some of you said, hey, just take cos 2a, replace it with cos squared a minus sine squared a, and plug in the values. You have to first find the missing values in the triangle if you're going to do that. Or you could use the equivalent expression for cos 2a that only has sines in it and plug in the sine value and then just, multiply by, add 1 to both sides and, multiply by 2 and then take that away from 1. Is that okay? Plug it in, but rearrange. Yeah. Oh, 6. Yeah, there was some trouble with 6. So I told you that, sorry, Josh, do you have your test? Did I give you your test? Were you here yesterday? Yeah. I have a test with no name on it, I think, and it might be yours. Is that yours? Okay, sorry. Okay. Oh, that's true. I didn't think about that. Okay, so in question 6, you were told that sine squared x is 8 over 9, and it said to find the value of sine 2x. Well, we know that the sine of 2x is just 2 sine x cos x. So we need to know what sine x is, and we need to know what cos x is. Sine x is fairly easy. We can just go from here. If we want to know what sine x is, just take the square root. And when you take the square root of a fraction, that's like taking the square root of the top. And the square root of the bottom. Sorry, I just forgot one thing here. When we take the square root, there are 2 answers. Where do we go from here? Make a triangle. Yeah, we know that this is the sine, so we know that the hypotenuse needs to be 3. If we're talking about this angle here, if we call this x, then the opposite side needs to be plus or minus root 8. So then we can use the Pythagorean theorem. I'm going to save us a little bit of time here and tell you that it looks like the Pythagorean theorem tells us that that missing side length is plus or minus 1. You don't have to use a calculator to do that. Here's how, Emily. We want to do the Pythagorean theorem, which would tell us that the hypotenuse squared is equal to the square root of 8 squared plus the other side. Let's call it, I guess it's this side here. The square root of 8 squared is just 8. So x has to equal 9 minus 8. Sorry, x squared equals that, so x has to equal plus or minus 1. So then we can jump back into here. 2 times the sine of x. The sine of x. Oh, thank you. Perfect. Yeah, I missed the interval there. It tells us that the solution has to be between pi over 2 and pi. That's this quadrant. We're not worried about sine being negative then. Sine is going to be strictly positive, which means, and same thing over here, we'll have that the x value, because we're in that second quadrant, the x has to be negative instead of positive, right? So the sine of x is going to be root 8 over 3, and the cos is going to be, did I write it down anywhere? No, I just wrote it down here. Negative 1 over 3. A lot of you forgot the negative there. 2 times, so we get 2 root 8 negative all over 9. Square root of 8. 3 times 3 gives us 9. The square root of 8, don't forget, we could write that as the square root of 4 times 2. Little review on the radicals. And the square root of 4 is 2, so we get negative 2 times 2, which is negative 4 root 2 over 9. All right, a couple identities. I don't know if I'll do all of them from start to finish, but I can give you a little bit to get started. Mr. Faulds came and had a look at the identities. He said, oh, these are all identities you can do in grade 11. I said, yeah, I know. It's a nice little early Christmas present. Yeah, we're going to go through it. I would say the first thing you want to do here is replace everything with sines and coses, because we've got some sines, some coses, some cosecants, and some tans. So let's just replace those. Yeah, we're just taking up the test. I was surprised to see how many of you had trouble with this. Well, kind of, yeah. And some of you had a hard time with the fact that there was a fraction in the numerator but not in the denominator. Don't forget, we can make this a denominator. And when we're dividing by a fraction now, we can actually just say, hey, let's divide the top, or multiply the first fraction by the reciprocal. So we get 1 over sine x times 1 over cos x, which is just 1 sine x cos x. Over here, we're going to have to find, there's only one term on the left. We're going to have to somehow...
Excuse the interruption. Will Haley Fenmore report to student services, please? Haley Fenmore.
Somehow have to find a common denominator here. The common denominator is going to be sine x cos x. So we'll have to multiply the fraction on the left by sine x and the one on the right by cos x. So that'll give us a sine squared x here plus a cos squared x over here all over sine x cos x. Sine squared x plus cos squared x is just 1. The left side and the right side are the same. We're done. It's really easy once you see it, but obviously making some of those connections is takes a little bit. Any questions about that one before we do the second one? Part B is, again, similar sort of thing where we have some tans and some sines. Probably the easiest thing here is to convert everything to sines and cosines. So let's replace this with a sine squared x over cos squared x. And if you were asking me on the test if you're allowed to do that, that tells me that you didn't really do much of the homework, right? Just saying. No, I'm just, it's a pretty obvious indication, right? I see one term on the right and two terms on the left. So let's try to turn this into one term. I would say multiply multiply top and bottom over here by cos squared. So we'll get a sine squared x minus sine squared x cos squared x all over cos squared x. So we've made it now so that we have one fraction on the left, one fraction on the right, but they're not quite equal. One thing that's really jumping out at me here is that there are only sines in the numerator here. There are no coses. So to me, it seems logical that we should try to get rid of this cos. It's a cos squared x. We can replace cos squared x with 1 minus sine squared x. Yeah, that works too. Perfect, yeah. And lots of ways to do these, right? That's even easier, I think, than this right here. Yeah. Because if you do it this way, you have to then multiply, distribute the sine squared x. So we'll get a sine squared x minus sine squared x. That's handy. So these are gone. We get a sine to the 4. Well, that's really the same thing as over here, right? Sine squared x times sine squared x is sine to the 4x. Good. All right, last page. Sorry. Yeah. Is that good? Does anybody want to see 8A? First one on 8? Okay. Is that enough, Emily? Is that okay? Okay. So cos x minus 1 equals negative cos x. I would say the easiest thing here to do is to collect all the coses on one side. It's kind of like, you know, having a one-step or two-step equation in grade 9. Let's collect all the cos x's on one side. So I'm going to add cos x to both sides. Cos x plus cos x is going to give us 2 cos x here. Let's add 1 to both sides. That will give us a 1 over here. Remember, our goal is to isolate for x. We want x on one side of the equation all by itself. So let's divide by 2. And we know that cos x equals a half. That looks like a special triangle. 1, 2, and a root 3. If the cos is going to be a half, we're talking about this angle down here, which is pi over 3. So the related acute angle is pi over 3. We want positive, so that happens here and here. Oh, you know why? No, I was going to say, no. You lost a negative somewhere. I don't know what you did there either.
Are those wrong?
They are, because you were looking for the negative one. Oh, I still gave you part. Your process was still okay. Yeah. I mean, if you had a positive 1/2 as an answer, you would have got the right answer. I think. I'm hopeful. So we need this angle in here. That's easy. That's just x equals pi over 3. And we need this one right here. Did I do that right? Yeah. Which is 5 pi over 3. Any questions? Okay. Next up, we had the 7 times the secant of x was equal to 7. Divide both sides by 7, and we get that the secant is equal to 1. Many of you at that point jumped out, changed the secant into cos. Well, if cos is in the denominator and we're trying to solve for x, it's probably a good idea to sort of flip this fraction upside down, which means that we can flip this fraction upside down as well. Again, if it doesn't look like a fraction, turn it into a fraction. The nice thing about, yeah, I didn't want to just write it as 1 because somebody would say, why can you just flip the one side and not the other side? But yeah, I just flipped this around, and the nice thing here is that when we do the reciprocal of 1, we just get 1, right? So it's not wrong, it's just not finished, right? That was the first part. So you divided by 7?
I subtracted.
Oh, whoops. Okay. It's not wrong. It's not finished. No. Remember the marks that you were saying earlier? I think he just gave me pity marks. You could apply those marks to that page if you want. So where does cos equal 1? If you look at a graph of cos, it equals 1, I guess, right here at 0 and at 2 pi. Any questions about that? All right, here's where things started to fall apart for many of you. Before we get too far here, oh, it's a negative half. Before we get too far, what's the period of this? What's the period of this function right here? What's the period of this function? Why, John? Compressed by a factor of 2. So that means that the period of this graph is pi, which means if we're going to go to 2 pi, and I think I asked for the solutions from 0 to 2 pi, if I remember correctly. Some of you found the solutions for the first part, but not the second part. So we kind of have to worry about that here as we go through this. So I started off by saying, hey, let's let a equal 2x. And then cos A is equal to -1/2. And we can do what we just did up above. The related acute angle is pi over 3. And we want to know, sorry, I'll continue on here. So the related acute angle is pi over 3. But don't forget we did this. We said that 2x is equal to a, so I'm just kind of going backwards and doing that substitution. Solve this, and we get that x is equal to pi over 6. Now remember, this is just the related acute angle, right? So this is like our related acute angle. So this would be the related acute angle if we were solving the equation cos A equals -1/2. We're actually solving the cos of 2a. So now the related acute angle actually has to be half of that value, which is pi over 6. And we are looking for a negative value. We want to know where is the cos equal to negative. We can do this a couple of ways. John already pointed out that the period here was pi. I'm trying to think how I should draw this or where I should draw this next. So here's pi. This value here is pi over 2. And then, so pi over 6 is going to be, well, here's pi over 4. And pi over 6 is going to be a little bit less than pi over 4. I'll put it here. So that's where one of the solutions comes. Where does the other solution come? Sorry, that's the positive value, right? That's positive, whatever it was, 1/2. But we want the negative values. We want this one right here and this one right here. How do we find those values? Well, if the related acute angle is pi over 6, here's another way to think about this. Normally we would talk about one complete cycle being 2 pi. Now one cycle is actually pi. So if we start here and we go all the way around, that's pi radians. It's not for the circle here that we're talking about this function. It takes pi radians to complete one full cycle. That means that pi over 2 is over here. Half of that is over here. Pi over 6 is over here somewhere. We want to know where cos is negative. Cos is negative in this quadrant right here, and it's negative in this quadrant right here. How do we find this angle right here? Pi over 2, subtract that pi over 6. And that shows up on this graph here, by the way. Shows up right here. Here's the pi over 2. This distance in here is pi over 6. This distance on this side, also pi over 6. So then the value of x, I should have used a different letter in here. Sorry, guys, because x is really equal to, what did we say, pi over 2 minus pi over 6? And x is also equal to pi over 2 plus pi over 6. Find a common denominator. We're going to get, what's that, multiplied by 3, take away, is this 2 pi over 3? Sounds about right. Oh, just 1 pi over 3. Sorry, where do you not understand what's going on still?
Like I just did it like the way that made sense to me. So
Yeah. Oh, okay, that's fine.
I did something really funny and I changed cos 2x to 1 minus 2 sin
Yeah, that was really funny.
squared x.
Still, did you get all 4 answers? Yeah, I think you did, right? Yeah. Yeah. Well, this is, sorry, let's finish this off. This is 3 pi over 6 minus 1 pi over 6, which is 2 pi over 6, which is the same as pi over 3. And then we can do the same thing here. I'll save us a little bit of time here, and we get 2 pi over 3. So we just found these 2 points right here. Yeah. Pi over 3 and 2 pi over 3. So that's here and here. We need to find these other ones. How do we find those other ones? We have to add the period because the process just repeats after the period. So here's one solution. Here's 2 solutions. The other ones happen at pi plus pi over 3. I'll let you figure that out. And x is equal to pi plus 2 pi over 3. I think that works out to actually 4 pi over 3 and 5 pi over 3. Did I do that right?
4 pi over 3.
Okay, is that all right? I could look at it after if you want.
I didn't use exact values, but like.
Yeah, and I probably should have said, I didn't say in the question, but I would expect that you should be able to do that using exact values. I didn't take any marks off, but because I wasn't specific. But if I ask you on the exam, be ready to do it in exact values. I don't know. Part D, I'm not going to do all of D. I'll just get it started for you. No, because D didn't involve exact values. One of the things that you should recognize or be able to do is to recognize when exact values are necessary or appropriate and when they're not. And in this case they're not. So again, I started just by saying, hey, this looks like a quadratic. So let's let A equal sine x. You don't need a formula. You can factor that.
I couldn't factor. I tried over and over and over again. I factored.
So it has to multiply to 72 and add to negative or add to positive 1. So I'm thinking 8 and 9. I think I have that backwards though. It needs to be plus 9a minus 8a. Yeah, so I was confused because I saw it as I was pretty sure it was factorable. Anyway, you go from there, you get your A values, there should be 2 of them, and then from there you would solve, go back into, replace a with sine. I'm going to skip a bunch of steps here. A is 2/3 and negative 3/4. So that means that sine x is equal to 2/3 and sine x is equal to negative 3/4. And then you can use, the CAS rule to figure out what the values are. And again, these values don't appear as special triangle values, so you would get 4 different answers, all as decimal approximations. Any questions on that? Second last question. Why is it possible to have a different number of solutions for quadratic trigonometric equations? Some of you explained why it's possible to have a different number of solutions for trig equations, but I specifically asked for quadratic ones. You could get 2 solutions. You could get anywhere from 0 to 2 solutions for a quadratic equation. So that could give you a range of possible solutions. And then for the trig functions, there are, if we're trying to find the sine x equals to 2/3, there would be 2 solutions there. So anywhere from 0 to 2 solutions as well. So anywhere from 0 to 4 solutions possible there when you solve a quadratic trig equation. Well, when you solve a quadratic, you can have 0 solutions. Solving a quadratic means we're finding the x-intercepts of the parabola. If we shift the parabola above the x-axis, there's no solutions. The parabola could come down and just touch the x-axis, which would give you 1 solution, or the parabola can come down and go through, having 2 intercepts, giving you 2 solutions. Each of those 2 solutions then would have 2 possible solutions for your trig equation. This equation right here has 2 solutions. Sine of x is equal to 2/3 in 2 locations. So we can get anywhere from 0 to 2 solutions for our trig equations and 0 to 2 solutions for our quadratics as well. So anywhere from 0 to 4 solutions for a quadratic trig equation. And the last question, just for Michael. Can a graphing calculator to be used to solve an identity? Yeah, sure it can. If we plot the 2 graphs and they lie one on top of the other, that tells you that the 2 functions are equal for all values of x. And remember, that's what an identity is. An identity is a statement that is true for all values of x. Left side equals right side for all values, not just one, but for all. And when you get the one graph lying on top of the other one, that tells you that that's an identity because it's true for all values of x. Michael? Typically, that's a good question. Typically on the exam, I'm more concerned about the mechanics. I think it's fair to challenge you with some of these sort of thinking questions during a test. During the exam, I just really want to see, can you do the work that we had to do? So, which may be an indication, Michael, that the exam will be easier than the test. Not easier as a whole. I mean, it's a lot of work preparing for an exam that covers 5 months worth of work. But yeah, if you look at just say the trig section, obviously we're limited by time as well. You had an hour to write, an hour plus to write every test. 3 hours should be sort of the maximum amount for an exam. So we're going to write whatever it is, 6 or 7 tests. I can't put the quantity of material on an exam that I would put on a test. Which is kind of funny. I almost wonder if I should be going backwards with that and asking you to do more of the thinking on the exam and less of the mechanics, because you've done the mechanics presumably and are good at that, and then I should be assessing your thinking. But anyway, it's not the way that I've done it. Okay, the last section we're going to cover right now is rates of change for exponential functions. Yep. No, I don't think so. Yeah, so this should look familiar to you. If it's not, I don't know where you've been for that whole course, but anyway, this should look familiar. The average rate of change, we could write it as f at x plus h minus f at x all over h. And remember that the average rate of change is just the slope of this secant connecting 2 points. I should probably write that down somewhere. Two points on a curve. Well, it's on a function, right? Typically, yeah, I guess it doesn't have to be. We could talk about say a function that was discrete, and instead of being, able to draw a smooth line through all the points, we would just have dots, and we could connect those two dots. But thanks for that. That's a good question. What's another way to think about the average rate of change? Yeah, we're just talking, again, I may as well focus on a logarithmic function since that's what we're looking at, or exponential. Logarithmic function looks sort of like this. Remember we talked about h being the distance in the x values between the 2 points? I think I missed there a little bit. So we basically find the y value at x, we'll call this x, I guess, and call this x plus h. Find the two y values there, subtract them, that's what the numerator is telling us to do, and then divide by h. Well, h is just the difference between the two x values. So another way to write this. This is the one that a lot of you forgot about on the last test, not the one that we just finished, but the previous one. The average rate of change is just the slope of the line, y2 minus y1 over x2 minus x1. Well, this says the same thing, but just written in a different way, right? This is the y, this right here is the y value at x, and this is the y value at x plus h. H is just the difference between them. So in some sense, it's maybe a little bit easier. What's the instantaneous rate of change? Yeah, so we introduce a limit, so probably worth jotting some of this down. The IRC, somebody said it's the limit as h goes to 0 of f at x plus h minus f at x all over h. What's another way to describe the, I mean, algebraically, there's nothing wrong with that. It makes a lot of sense. Say that again. What about the tangent? Yeah, it's the slope of the tangent. So it's the slope of the tangent at a given point. And if we look at a graph, if I want to know the IRC right here, we find the tangent, we draw the tangent in. Again, the tangent is a line that just touches the curve. And then we find the slope of that tangent. Looking at this, we can see that the one that I've drawn is positive. Pretty hard to get some values on there since I didn't include any values. Here's the trouble that we're going to run into. If I do this for a log function, let's say we just do log x. And if we want to find the instantaneous rate of change of this function, we would do the limit as h goes to 0 of f at x plus h. So that's going to be the log of x plus h minus the log of x all over h. So if I ask you to continue that, where are you going to go from here? What's that? Yeah. What values? Right, except now I'm asking you for just the function that represents the rate of change at any given point. Now I haven't given you the point, and you're right, once I give you a point, x equals 5, we should be able to plug a 5 in here, but there's still a bit of a problem. Leslie? Yeah, so the problem is that remember that when we did this for the rational functions and the polynomial functions, we were able to divide an x out of the top and the bottom. We factored in sorry, not an x. We factored an h out of the numerator, and then we were able to divide it out of the numerator and denominator. At which point we were able to substitute a 0 in here. We cannot factor an h out or remove h from this log at this point because you guys just don't have the background to be able to do that yet. Right, right. So what we need to do is we need to do the same thing that we did for the trig functions, and we're just going to estimate the instantaneous rate of change. So when we did the trig functions, we talked about how we could do that. We could do it two ways. One was this way here where we could draw in, if I asked you for what is the IRC at x equals 5, you could draw in, actually draw the curve and then draw in the tangent and then figure out the slope of that line. It would, eventually go through a couple of points, or you could estimate the values at a couple of points. So you could calculate the instantaneous rate of change there. Or the other option is we said, hey, let's just choose a point that's really, really, really close to the point that we're given and find the slope of the secant there. And that will be an estimate. And it is just an estimate. And depending where you are on the curve, it's going to be, it might be a better estimate than others. Where do you think using this method of choosing a point really close is going to be more accurate on the graph of a log function compared, well, yeah, where do you think it's going to be more accurate, and where do you think it's going to be less accurate, and why? More accurate here? Like down here? More accurate out here? How come? It's going to be really, really steep down here, right? Like the rate of change, if I ask you for the rate of change here, you can see it's like this. If I ask you for the rate of change here, it's quite a bit more, right? So the rate of change looks like it's actually changing, if you can think of it that way, the rate of change of the rate of change. Well, this is getting pretty deep here. But it looks like it's changing more. So we're probably going to be more accurate with this estimate. Sort of up in this section of the graph rather than down in this section. But we're going to use it as an estimate anyway because it's the tool that we have that's available to us. If you wanted to be more precise, you could actually do what we talked about earlier. Draw the graph, plot the point on, and then draw in a tangent and find the slope of that tangent. But for us, let's estimate it. And we'll use h equal to 0.001. Again, if we're all being consistent here, obviously if you wanted to be more precise, you could use a smaller h value and get a more precise value. Another thing you could do that I know we maybe touched on a little bit in the last unit, but I didn't actually have you do any work like this. You could actually find the rate of change from here to here on the right. So you could say h is going to go to the right. I'm going to choose a value there. And then you could actually take another value over here, an h value in the other direction, and then like find the average of those two rates of change. That's a possibility too. I think that it would be more precise. It kind of doubles the amount of work that you guys have to do. As long as you get the idea, I'm not going to make you do any more work than you need to do. So that's rates of change. I mean, I'm not going to do an example because you guys have done these examples over and over and over again. The only difference is that now we're going to be using the log function instead of the trig function or whatever other function that you may have done. So here's the work for today. So here we go, page 507. These are all fairly easy, but let's do 1 to 8. I was just going to add to it, John. You can always add more. No. Just 1 to 8, I think. Yeah. there aren't really any parts in most of these. I mean, there's like an A and a B, but all right, that's it. That is the last lesson before the